we can form more than 4 groups, so that we discuss with your class reps, that we see, so that you start your revisions or research in those groups. So some of the references that you can use, Sadiku is a very good book to use, especially if you want to look for examples and very simple explanations that are given there, elements of electromagnetics, and many other books that have microwave devices. So as we said, so we'll be tackling design of waveguides. Of course, the syllabus has changed a bit for those who are in third year now, but for you it will remain the same as what was there before. So currently we'll have the design of waveguides, where we look at waveguide shapes, how you can excite a signal in the waveguides, the power that is delivered at a point in there, and how you couple it so that it delivers to the antenna. Then we also have design of cavity resonators, which I'll see whether I'm the one to handle that. And then we have impedance matching in microwave systems, and then active and passive microwave devices and systems. So we know that at very high frequency, if we talk about 3 to 100 gigs, that those frequencies, the conductor resistance and radiation leakage are high. So we use the waveguide to alleviate those losses. And also, if you want to multiplex in a more simple way, then you need to use the waveguides instead of conductors. And you need to explain that. Why is it that at high frequencies, then the radiation leakage will be high in conductance? So here you can remind yourself of skin depth. See, when you're propagating, try to use my pen. Okay. So we'll have let's say that is the transmission medium that you have, and you know the propagation, about 63% will be propagating at the surface. So that's what we call the skin depth. And if you can remember, what is the formula for skin depth? Actually determines the attenuation constant. So you have, sorry, it's not going to be easy for me to write. I'm writing with the left. So pi f nu times the conductivity. So what do you see there? When the frequency is high, so this is going to be a bit interactive. Can somebody tell us what happens to the skin depth when you have very high frequencies? Where will the signal be confined? Is it towards the surface? Is the surface here or away from? At very high frequencies, where would the signals be confined? You can see it's inversely proportional to the frequency. So then it means the waves will actually be closer to the surface as compared to low frequencies. And that's why you have your radiation leakage, okay, in conductors. But for the waveguide, let's say you have a rectangular waveguide. So it's a hollow structure. So the way it is constructed is such that there's high permittivity inside as compared to the outside. So what would happen is that when the waves propagate, when it hits there, it is reflected back inside so that it achieves total internal reflection. Okay. So in that case, you can see that we will be avoiding radiation leakage if we use a waveguide rather than using conductors, and that's why it becomes very important. In terms of the structure, we normally just use the geometry to determine different types of waveguides. So you can have circular waveguides. Definitely the mathematics for different structures will be depending on the shape, which means the coordinate system that you are going to use. If you use rectangular, then you use a rectangular coordinate system, Cartesian. And if it is circular, you use a cylindrical. And if it's spherical, you use a spherical. So here we would just be revising. So you will be able to see on that reference some analysis on circular waveguides, but we will, for our case, we will be working on with the rectangular waveguide. Okay, you also have strip lines and flexible waveguides or a ridge waveguide. So depending on the application that you want to use your waveguide on, then you will be using different shapes to achieve those specifications. So the width of the waveguide is normally desired to follow the wavelength of that wave. So it means you need to confine the wavelength within this hollow structure. So that tells you that the design of the waveguide will depend on the frequency in which you're operating. So if you have a certain frequency, you have to compute the wavelength and make sure that it is within the size of that waveguide. So you may want to, isolate some signals or attenuate them, amplify or circulate them somewhere, or mix them. So you can use terminations on the waveguide to be able to achieve all those. So you make sure that always the width of the waveguide is in the order, the wavelength. Even fiber optic is a waveguide. Actually, everything else that you use, you can decide and call them waveguides. But here we are confining ourselves to the hollow structures. All right, so sometimes they use silver plating on the conductive wall, which also cuts down on any resistance that may be on the wall, because then that brings the impurities of the waveguide. So the electric material is normally of high permittivity is placed inside an outer dielectric of lower permittivity to achieve the total internal reflection. Okay, so it will confine these waves inside the physical boundary. So the waves now do not obey the distance law, the inverse square law that we normally talk about, because of this total internal reflection. So what about if it were optical fiber? We'll be able to discuss this more on our tutorials. So if it were optical fiber, also we use the same, a dielectric material of high permittivity to achieve high refractive index. So the outer, we put a lower permittivity, again to achieve total internal reflection. So that's we will be able to see when we are discussing different types of waveguides. So the components of a waveguide can be there. You can use isolators, attenuators. You'll be able to see this in the lab. I think probably you saw it when you're in 4th year. Circulators, mixers, and loads. Okay, and here you need to define a few concepts when we talk about group velocity, phase velocity, attenuation constant, the guided wavelength, wave impedance. What are these concepts? All right, so, and also cutoff wavelength. When you talk about cutoff frequency, how do you excite different waveguides in different modes? How do you couple them, suppress? How do you then calculate the amount of power that is delivered at a distance? So that we'll be able to see as well when we discuss this on the tutorials. It's easy on the tutorial because we're just doing revision, so it means you probably have done them in the 4th year. So I want to concentrate on the modes of the waves, where we call about, some of them are transverse electric waves, some are transverse magnetic, and then transverse electric and magnetic. So you can see that transverse electric, definitely here we are talking about these waves not being in the path of propagation, but are actually 90 degrees out of phase to the path of propagation. So when we say TE, so it means the electric field is the one that is transverse. So what does that mean? So in a transverse electric field here, we will be talking about if you have X, if you use rectangular coordinate system, XYZ, then it means for the transverse electric, what does that mean? It means the direction of the amount of E in the Z direction is equal to, can somebody try?
0.
It's equal to 0. Okay. And then when we talk about transverse magnetic, what is the value of Hz? So in the transverse electric, what is the value of Hz? Wainaina says 0. Okay, that's for the first question. But for the second one, what is the value of Hz in transverse electric?
It's not 0.
Not 0, correct. So Hz is not equal to 0. Here, Hz 0. What about Ez? Not equal to 0. And in the time waves, transverse electric and magnetic, it means both. Anyone for the term?
Both Ez and Hz are 0.
So for transverse electric and magnetic, so we have Ez is equal to Hz equal to 0. Okay, so we have the transverse direction being XY, or if it was cylindrical, we're talking about R and phi, but the longitudinal direction remains as Z. So if you remember your coordinate systems. Now we will just look at Maxwell's equations and try to see how different modes can be operated from, of waves can be operated from a waveguide. So remember the curl equation for Maxwell. We normally have the cross product of H or E. It's equal to minus d over dt of B, magnetic field density. So we can write dt of, we know this is mu h, isn't it? So that's mu h. D over dt, we like, you're covering 2 pi, the distance 2 pi over some time, if you say on the period. So this would give us omega. But the cross product, when you do a cross product, what do you have? The result will be orthogonal to that plane. So if you have this cross product there, so the result will be in this direction. So it's 90 degrees, which you can express as J. So that's why we're saying now, if you have the cross product cross of E is equal to minus d of B over dt is partial for all the directions. So it means then we can write this here as J minus J omega mu h. Now we want to look at the components of X. remember, you can take note. The cross product, if you remind yourself, is we normally just write the determinant. You can have vector x, y, z, then d over d, this is del over the x, del over the y, del over the z. Then we have x, ey, ez. So we want to determine this. You see that j omega mu h. So when you want to determine the x component, what do? We use the other two by 2 matrix. So we want to determine the x component. We are going to use this. Okay, so the leading diagonal is dy. The leading diagonal would be, so here we have, remember, depending on what method you use, so we have plus, minus, plus. So if we want to determine the x component, we'll have this d over dy of ez, the leading, minus the lagging. So it's minus d over dz of ey. So that's what we have here. Then the y component, we block the y, but we know we have a minus here. So we'll have this, the leading, d over dx times ez minus d over dz of ex. But remember, we have a minus here. So that's why we have here negative and here is positive. Then for the z component, so we just block that. Then we have d over this x of ey minus d over dy of ex. And that's what we have. So that's how we determine those values from the cross product of E, where we are saying all the components exist in the x, y, and z direction. So if that's clear to everyone, we can proceed. Did I share this note? This one, this document?
Yes.
Okay, good. So you can follow from there just in case you have a problem. So let the wave propagate with an exponential decay such that we have this value here. So you have e raised to negative j beta z. Beta there is the propagation constant. So if we get the derivative of that value in the z direction, definitely, then we'll have minus j beta times that same exponent. So in that case, we can rewrite what we are seeing in question 1. D over, okay, either it's d or del because it's partial. D is z over dy. Then we can see any derivative with respect to z direction. That's what we are taking. For in that case, we have d of ay over dz, because here we are doing a dz. So that's what we are talking about. So that's the one we are changing. So d of ey over dz, we have seen we can rewrite it as minus jb beta times e minus jbz. So it means then if we write just the vector ey, so we have minus j beta times this value here, d over dz, which is minus, so it will be positive j beta ey. So we can change that first part of the equation here. So it becomes this. Again, here we have anything that is over dz is dEx over dz. And because it's negative, so it will give us that value. Then we have the last one, we don't have any the derivative with respect to z, so we'll just have the same equation. So we have 1, 2, 3. You can do the same thing for cross product of H. Normally from Maxwell's equation, what do you have in the as the product, the cross product of H is equal to, the point form is, you can derive it from here in terms of field density. Can somebody tell us?
DDTD.
DD over DT, isn't it? Okay. So the same way we can see d over dt is j omega, and then d is equal to epsilon e. So that's why we then have that value there. So we can follow the same procedure. These are just for illustrations. Don't worry, you're not going to be asked to derive all this. So just for illustration. So del hz over del y plus j beta hy is equal to that. We do the same what we have just done previously. You'll get these values. Okay. Then you try to, you can consider computing the transverse components only of E and H. For example, here from the first one, we have dEz over dy. Because what we want here, we want to get the transverse component hx from 1. So what will we do? So hx plus of 1, you can see you divide everything else here by minus j omega u. Okay. So you'll have j over omega u into whatever is on the left hand side, d of Ez over dy plus jb ey. Okay, so that's from 1. But now we can substitute ey from 5, because now we know ey here. Okay, so you can substitute that ey there, because what we're trying to do is we're trying to express all these equations for the transverse components in terms of z direction only, the z component. So we want the transverse components computed from the z component only. So that's why we are doing that. So you replace all the transverse components. So ey from 5, you replace it. So you'll compute hx is j over omega u, just what we have here, dEz over dy plus jb ey, but ey is the whole of this. Okay. So when you do that computation, what you will end up with is a function here, which can be written as 7. So j over kc squared into omega e dEz over dy minus beta dhz over dx. What you can see is that now hx is expressed in terms of Ez and hz. For now, k, just call kc is k squared minus beta squared. We'll see why those are written like that. Then hy, the same. So what is important, when you follow all the same procedure, you'll actually realize that you have just the longitudinal components. Okay. So what that means is that from 7 to 10, all transverse components of E and H can be determined from the axial components E, Z, and HZ only. And that is why it is now possible to classify the waves at either TE mode, TM, or TEM modes. Okay. And we say it for transverse electric, it is Ez that is going to be 0. So if you can, anyway, that is the statement, that the transverse components E of E and H can be determined from the axial components. Probably you met that again. I don't know how much you covered in the 4th year. So for TE mode, we can now look at TE mode. As I said, you are not going to be asked to derive this. It's just for illustration. So if you have a TE mode, we know that the wave has Ez is equal to 0, but Hz is not equal to 0. So the E components are transverse to the direction of the propagation. So long as you have Hz, you can see, so long as you have Hz, look at these ones here. We have said that Ez will be 0 for the transverse electric mode, isn't it? So if Ez is 0, it means this first component, this is going to be 0, 0, 0, isn't it? Because we are saying Ez is 0. So it means then we can now only write the equations for the transverse components for the TE mode in terms of Hz only. So that's why we are saying here, for Ez equal to 0, we use 7 to 10 to determine the components of E and H as long as Hz is determined. And that is true, you can see. So long as we have Hz, we are able to compute those components. From all that, you can actually show that now Ex, for example, we can have Ex, Ey, Hx, Hy. So after long computation, this is never true, this statement, that it can easily be shown. It's not very easy, but anyway, it's a long process. So you can show that Ex can be written as j omega mu over kc squared into n pi over b h naught cosine n pi over ax sine n pi over by. Then where now we have introduced some constants there, m and n. So the number of half cycle variations in the field in the x direction will give us m, and n is the number of half cycle variations in the y direction. That means you are able to see the field inside the waveguide in this sense. So let's say you have a rectangular waveguide, and we want to say so we are saying y and x direction. Let's say you have x and y. Let's say we want TE, MN. It's TE. Let's say how many? Let's give an example, maybe 3, 2. So half cycle variations in the x direction are 3. M is equal to 3 and n is equal to 2. So how do we show that? So the field, when you look at the field and the propagation, let me use blue. So you have half cycle, 3 of them. So you have 1, 2, and have half. Those are 3. Then we are saying you have, I drew very small, but it's okay. So there are 3 on the x. So it means here we'll have a full one. Full. Then we have half. Now you can see we have 3 full variations in the x, but we need 2. So far we have 1.5 on the y direction. So then we'll have another half here. Then we have that. 1, 2, should be 3. So half. So it means here we need to have this y somewhere here. Okay, so looking at the field inside the waveguide, this is how the waveguide is a rectangular one. Okay, so z direction is there. Okay, so you're looking at the end. So you look at how those fields are flowing, definitely then you have arrows showing. If you have that, then it means here also will be the same. If that is there. Okay. So that's what determines. So it means when you're exciting the wave inside this waveguide, you can do it at different modes. You can do a TE11, a TE10, a TE34. Okay. So depending on how you excite the waves inside that waveguide. So that's what we mean by half cycle variations. Okay. So you may be asked to show that you have this understanding by sketching maybe end view of a TE2, 2 or a 10 to demonstrate the half cycle variations on that waveguide. Then that is for EX. Then EY, I want you to note how we are moving from N to M. But don't worry about that again. We are not, for me, fifth year is for applications, not for knowledge in terms of deriving theories. So here you have N pi, here you have M pi, pre-multiplying. So this is like an amplitude, you see that? Then we have sine times cosine. So n pi, m pi, m again for hx, then hy we have n. So you can derive ex, ey, hx, hz in this equation. So then we can try to see, is it possible to excite a TE00 mode? Looking at those equations. So what we are going to do is try to place on this amplitude here. If n is a 0, this will go to 0, isn't it? Here, if m is 0, that goes to a 0. If m is a 0 here, goes to a 0. N0 goes to a 0. So definitely, of course, if you have the mode as 0, 0, it means you have not excited it. That's what it means. But that will be important. What we are trying to do will be important when we look at the TM mode. So for propagation constant, remember, we have here no attenuation. We assume there's no attenuation. So what would happen when we are writing the propagation constant? This is just the point at which the wave begins to, we want to determine the cutoff wave number. So what we are saying is there's a certain frequency at which the wave begins to propagate. What does that mean? Remember, beta is omega over c. So at cutoff, when the wave just begins to propagate, what does that mean? It means that we can write, here we have the propagation constant. We can actually equate that at that point at which it just starts to propagate, what is the value of beta? When it just starts, it just begins to propagate. It means that is the point at which beta was actually 0, isn't it? Because it's just beginning to propagate. So if we equate this equation, 15 to 0, what do you get? So you will say that omega, so at that point beta is equal to 0, so you'll have omega squared mu epsilon is equal to m pi over a squared plus n pi over b squared. Now, in this, normally we denote the length of the waveguide in the x direction as a and b for y. And conventionally, we will always take that a is more than b. Then we have here 1 over mu epsilon is equal to actually the root of that is equal to the velocity of the wave. So we know that c is equal to 1 over, that's the expression for c. So we can divide we have it here. C is 1 over root of mu epsilon. Then what we'll have is that omega squared, which is 2 pi f squared is equal to one over c squared m pi over a. Remember, m is the number of half cycles in the x, n pi over b squared. So remember, here is the cutoff where we have equated the propagation to be just leaving 0. So it means it's just getting to propagate. So that's then we are saying this is actually FC, the cutoff frequency. So what do you have as FC? You can divide both sides by 2 pi squared and get the square root. So that's why we are able to derive this one here. Okay, so the cutoff frequency. Can somebody now tell us what the cutoff frequency is? How would you say, how would you define it? What is cutoff frequency if somebody asks? Is the frequency at which the wave just begins to propagate forward within the waveguide. The frequency at which it just starts to propagate. So it means for waves to propagate inside the waveguide, it has to be at least, the frequency of that signal must be at least the cutoff frequency or higher. It has to be at least the cutoff frequency or higher. But if you want to determine it in terms of the wavelength, we know that the wavelength is c over fc. So how would you define cutoff wavelength?
It is the maximum wavelength.
It's the maximum wavelength. Yeah. Good. So cutoff wavelength is the maximum wavelength which occupies the length of the size of the waveguide or the width of the waveguide. So it's the maximum that will actually be within the waveguide because your waveguide is like that. So you must have the cutoff wavelength, which is the maximum that you can have within this waveguide. If you have a larger wavelength, then it will be going beyond the size of the of this waveguide. So it means you are going to lose some of your signals. So they're going to be attenuation. So it's the maximum that can propagate within the waveguide. For cutoff frequencies, the minimum. So it means you need the minimum or higher. For cutoff wavelength, you need the maximum or less. All right, so you can see how cutoff frequency and cutoff wavelength vary. What about the dominant mode? Now you see, depending on the mode, where we are saying TEMN. So it means we can use this function here to actually produce different cutoff frequencies for different modes, isn't it? Because it's dependent on M and N. So we can have TE, M, N. So we want to compute FC, the cutoff frequency, such that we look at which one has the lowest cutoff frequency among different modes. So you can have M, we know we can't have M being equal to N equal to 0. This one we can't have, we saw that everything else will be 0. But Mn can be 0, 1, 2, 3, any integer. So we can compute different cutoff frequencies for different modes. So FC, TE, 0, 1 can have 0, 1, so M, N. Did somebody ask anything or somebody joined? So you have 0, 1, 1, 0, 1, 1, 2, 1. You can go on and go on, okay? So then, so you have the TE modes, and then you compute the cutoff frequency. So you realize that one of them has the lowest cutoff frequency. So that one we are going to, if it has the lowest cutoff frequency, what would you say about the cutoff wavelength? The mode with the lowest cutoff frequency has what kind of wavelength?
Has the highest cutoff.
Yes, it has the highest that just fits within the waveguide. Okay, so we say it is dominant. You can see the highest is the one that actually fills the whole waveguide. So that's why we call it the dominant mode. So the mode with the lowest cutoff frequency or the highest cutoff wavelength is called the dominant mode. And when you do this computation, you will realize that it is TE10 mode that is the dominant mode for TE modes. And remember we said that A is always bigger than B. So from field equations, TE10 is the minimum possible mode that results in a non-zero expression for those expressions that we have for rectangular waveguide. So TE10 is the dominant mode with the largest cutoff wavelength. And we say A is more than B. And now you can calculate the dominant frequency, isn't it? Either you can always be used to this or you can always reduce it. Because now we are saying N is equal to 0 for the dominant mode. So if N is 0, because it's a TE10, and we're talking about TEMN, so we have FC TE10 is equal to 1 over 2 root mu E epsilon, but M is 1, and we have A squared, so 1 over A. So you get that square root, you reduce that equation to this, the dominant mode. Anyone who can't see that? You can reduce it to that for the dominant mode. That's not very important, just that's maths. Okay. Yeah, because sometimes it can be confusing. Sometimes you forget, and then you better just have this, master this full equation for the cutoff frequency. Okay, so it means then we can have an example and see.
Excuse me, sir.
Yeah.
It is said that the cutoff frequency is actually obtained when the propagation constant is kind of 0. How can that be proven?
Cutoff frequency, what you do, you just use intuition in this case. There's no proof you need there. What we are saying is that you have wave equations, isn't it? Okay, you have wave equations that from Maxwell's equations. So you have theory. Okay, you have your wave equations here, assuming that there's propagation. Okay, which you can reduce and determine the propagation constant as this. So what we are saying is that the cutoff frequency is the frequency at which the wave just begins to propagate forward in the waveguide, isn't it? When it just begins to propagate. What does that mean? It means from the wave equation, which is generalized for propagation, you can assume that at that point, there was no propagation. I didn't see the name, whoever asked the question. Who was that?
Davis.
Davis, yeah. So we're just saying at that point, do you agree that at that point, there's no propagation? When it just starts to propagate?
Yes.
So that's what we are saying. So we equate equation 15 to that. We say at that point, beta is equal to 0. Is that enough reason for you now to see what we are doing? Or what proof would you want?
Yeah.
You get it, eh? Yeah. So that's what we have. So you're saying at that point at which there's propagation, actually there was no propagation. So that's what because these are generalized equations for propagation. So that's what we have equated to get that cutoff frequency. If you want to prove it, just derive it by equating this equation here to 0. Equation 15. All right. So if you are satisfied, that is important because when you're using these equations, you need to apply some knowledge to it to be able to get to the applications. So let's say X band, this may not be accurate. Let's just say that you are considering some air-filled waveguide with known dimensions where A, and we have agreed that A is in the X direction, B is in the Y direction. So you can sketch your waveguide, it's a rectangular one. So you are asked to determine the first 4 modes of waves that will propagate in the waveguide. So what are we supposed to determine here? We need to look at the cutoff frequency for those, for the waveguide, and see which one lies outside the band that we want to use. So here you are doing maybe link planning and you have certain frequencies for the equipment that you have. And now you want to determine if you have restricted yourself to a certain waveguide of certain dimension. So you just need to see what mode should you excite within that waveguide, which you already have. You can't change it. And you want to see whether it falls within the frequency bands that you have. So as an engineer, you need to determine. If it is air-filled, no dielectric loss within there. So you have your dimensions A and B. So if this is your X, so each time, I think I stressed this even in your third year, what you do is that make sure you always sketch whatever it is that you're doing. So you have A, then you have B in terms of dimensions. So determine the first 4 modes of waves that will propagate in the waveguide. So if you have your calculator, let's see, you can use your calculator from anywhere, your phone or whatever. So you're supposed to compute the cutoff frequencies for different modes. And we want the first 4 modes of wave that will propagate in the waveguide. So it means you need to determine the cutoff frequencies of those different modes and see which one falls within the X band that you have. So here we are saying approximately 8 to 12 gigs. So you start with TE modes. So we have TE modes MN. You can get the FC for MN0, 110, 11. Then you go to 20, 21. You can have 12. And let's compute the first one, TE01. Can you confirm if you're able to get that value? TE01 using this equation here. So we have said that 0, 1, m is equal to 0 and n is equal to 1. C, because mu r and epsilon r is equal to 1, so you can use the conventional value for C. 3 times 10, 8 meters per second. Then you divide by that 2 and then get the square root of those values. A is given 2.3, B is given 2.3 centimeters. You remember we have to work in meters. Let's have some answers for TE01. Is there anyone who has computed?
TE01 is 14.71 gigahertz.
Okay, so you computed 14.71 gigs. Anyone else? Okay, so you can see it's close to the answer we have here in the notes, 14.8 gigahertz. Then you compute TE10. 10 is easy because we have just one value. Can somebody then compute TE10? So n is equal to 0. It should be quick.
TE10 is 6.5 gigahertz.
Okay, 6.5 something gigahertz, depending on whether you used. Okay, right. So again, very close to what we have, 6.6 gig. All right. So anyone who has computed TE11?
16.1.
16.1. TE20? So 16.1 is close to 16.2.
TE20 is 13 gig.
You get 13 gig, yeah? All right, which is close to 13.1. So right, so these answers we have here are good. So then what we see there is that we are saying the mode should have a cutoff frequency which is below the frequency of operation, isn't it? So the wave that we're injecting in that waveguide should have a frequency that is higher than the cutoff. So if the cutoff here is 6.6 for the TE10, it means there will be propagation without attenuation, because you can see that the TE10 has the cutoff 6.6. So any wave that is above that cutoff, which we are talking the X band, 8 to 12 gig. So those are higher than the cutoff for TE10. So it will be able to propagate forward. The cutoffs for the other modes for 01 is 14.8. And you can see the signal that is coming in 8 to 12 gigahertz will be lower than that cutoff. So there will be no forward propagation for TE01. What about TE11? The cutoff is 16, which is higher than what you have, 8 to 12 gig. The cutoff for 20 mode is 13.1. So it means for what you have in your lab, you have a waveguide which is this dimension, and you want to operate in the X band. Probably you are only licensed to operate in the X band, 8 to 12 gigs. It means the only way you can apply what you have is to excite the TE10 mode inside that waveguide to be able to have forward propagation. Is it clear to you, everyone? So here is just a single mode operation in the X band for the dominant mode TE10. So you can see it is the one that has the largest wavelength inside that waveguide because of the low frequency. So it's only a single mode operation in this one. We can also look at the equations for, because that was TE. Remember, we didn't derive them. We said you can show that you obtain these equations here, just to illustrate. The same way we can show for TM that TM mode, which is the transverse magnetic, meaning the Hz is equal to 0. So we can also, again, this statement here is just to mesmerize you. We can show that EX, EY, HX, and HY can be written in this form. But now you will see that there's a difference here. In the amplitude, now we have EX, we have M, EY, N, HX, N, HY, M. So we want to try, now that we know that the dominant mode in the TE propagation mode is 10, meaning we have M equal to 1 and N equal to 0. Now we want to try and see whether in TM mode we can have a TM10. We want to see whether we can have a TM10. Now let's start with equation 1 for EX. When M is 1, the amplitude exists, isn't it? That's okay. Cosine will exist. But remember, our N is a 0. So here we have 0. What would happen to EX? Somebody? We are trying TM10.
It will vanish.
Vanish, isn't it? The whole, yeah, so it will be 0. TM, sorry. How do we go back here? Okay, can I erase? TM10. So EX will be 0. Then we go to EY. EY, because N is 0 here, EY will vanish also, isn't it? Because that's the amplitude. Then HX, so long as N is 0, vanishes. Then HY, M is 1, so that's okay. 1, then we have a 0. Again, HY vanishes. Then we have, so here we already see that we can't have a mode TM10. So we had the mode TE10, which is actually the dominant mode. But now for the TM10 does not exist. And that makes sense because normally the electric field produces the magnetic field in the transverse direction. So they are orthogonal. Now, then we go to, which one do we try? Let's try TM01. 0, 1 means m is equal to 0 and n equal to 1. So when m is equal to 0, ex, what happens to ex when m equal to 0? Can somebody see it?
It vanishes.
That also ex vanishes because m is equal to 0, the amplitude there. So it doesn't matter what the shape of the signal. And then we have in EY, we have n equal to 1, so that exists in the amplitude. M is equal to 0, sine of 0 becomes 0. So again, it makes EY vanish. Hx, n is equal to 1, m is equal to 0. Again, sine of 0 there vanishes. And here, m is equal to 0. Again, that vanishes. So all of them vanish. So what we are seeing is that for TM mode, when either m or n is equal to 0, then E and H will be equal to 0. So those modes are not possible in the TM mode. Now let's try to determine another. Now that we have seen those modes are not possible. So we can, the same equation for cutoff frequency, of course. But exciting those modes are not possible. So we want to consider another air-filled waveguide with certain dimensions. A is equal to 2.3, B is equal to 1.02. And determine the first 3 TM modes of wave that will propagate within the waveguide for that band that is given, about 13 to 32 gigahertz. Again, it's air-filled, so we just have mu r and epsilon r is equal to 1. So cutoff frequency, the same formula. So we know we can't have TM mode 0 something. So then we just have TM modes, TM, MN. Then we can start MN. We can have 1, 1, 1, 2, 2, 1, 2, 2. You can continue. Now you need to compute the FC or lambda C for those different modes in TM. So somebody can do the TMFC for TM11.
Excuse me, sir.
Yes.
Could you scroll to the A and B, the coordinates?
No, A and B. Also here we have A. A is 2.3 centimeters. B, 1.02 centimeters. What else do you need? That's all.
Yes.
Mhm.
TM11 16.1.
You get 16.1
Yeah.
gigahertz. Okay, which is close to 16.2. Then 1, 2.
30.1 gigahertz.
30.1 gig. So about that, 30.2. Then TM21.
$19.7.
9.7. Okay. So what about TM22? Though we will ask for 3, just do the 22.
32.2.
32.2. Okay, 32.2. So this one will fall outside. So you're saying this is 32.2 gigahertz. So can you comment on the mode of operation of the band? In the band. These are the cutoffs. You remember CAK has licensed you to use only 13 to 32 gig, all right? And you have bought a waveguide of dimension 2.3 by 1.0 rectangular. And you need to excite your signal such that you are able to have forward propagation within the waveguide. So which mode would you use to be able to achieve that? That's the question. You have that band 13 to 32. Which mode would you use to achieve propagation within your waveguide, which is fixed?
The dominant mode can be used because it's 16.2, and the TM12, and also the TM21.
So all of them can be used.
Yes.
Correct. I hope everybody is seeing that. What about TM22?
TM22 is 32.2, so it's beyond the.
So the cutoff is beyond the range that you have, isn't it?
Yes.
Yeah. So it was important to calculate that fourth one so that we see that it's beyond the band that you have. So the cutoff, the frequency of the signal must be higher than the cutoff frequency. In our first case, your frequency was 12. The only one that was below 12 was the TE10. But in this case, all these cutoffs are below 32. So it means if you have a signal of that frequency of 32, you can actually use it to achieve propagation. So all modes can operate. And the dominant mode is TM10. So the dominant mode here is the one that has the lowest cutoff frequency. Now, we have not computed other modes like 2, 3, 3, 2, and all that. Do you think in this case, TM11 is the dominant mode? Is it true for all the modes in TM that TM11 is the dominant mode? Or if we calculate other modes, we may get it dominant, other dominant modes? Do you think TM11 is the dominant mode? Or we need to do others so that we are sure? From this equation here.
Yes, it's the dominant mode.
It is the one that will give us the lowest, isn't it? Because you can see the cutoff frequency depends, it's additional. So it depends on the value of M and N. So we just need the lowest value for M and N to get the minimum frequency. So if you go higher, because there's no zero, so long as M or N is equal to 0, then we won't have the propagation in TM. So if you look at that equation, you see that M and N, the least value is when they are 1, 1. So that will give you the dominant mode. So TE10, between TE10 and TM11, which one do you think would be the dominant mode for all waveguides? Between TE10 and TM11, 1. Which one would be the dominant mode using that equation for FC?
TE10.
TE10 will give you a lower frequency than TM11, isn't it? So then in this waveguides, now we can conclude that the TE10 is the most dominant mode. Now we note that from those equations then, F must be large enough so that the propagation constant beta is actually a real value. Okay, because we remember cutoff, we equated it to 0. So for it to be real value, then this value here must be more than that. So questions can come in either way, but with the exercises to the tutorial will help you see how different approaches, but the fundamental remain the same. We either use that final equation for the application. As I said before, you tune your mind in the 5th year towards applications. So we'll be using the final results to determine what we actually need in the field. So you'll be thinking more of an engineer than a researcher. So it's more of how do you apply that equation, or how do you apply the cutoff frequency or cutoff wavelength to achieve certain designs. What about TEM mode? I think we can look at that before you close. These are just introductions. You'll be easier when you do the tutorial. So TEM mode, what do we say about EZ and HZ? They're both equal to 0 because you're saying it's transverse, electric, and magnetic. Who can explain why there's no cutoff frequency associated with the TEM waves? Remember, the propagation is in the Z direction when we are talking about transverse electric and transverse magnetic. But the TEM mode, what we know is that you need is not a hollow waveguide. So a hollow structure will not be able to support a transverse electric and magnetic wave. So at least you need at least 2 separate conductors for you to be able to achieve TEM waves. So you can have a coaxial cable or a parallel plate or a strip line or a microstrip, which you can use on PCBs. Some of them are very small. It's not something you see physically like the waveguides that go to the antennas in the BTS. You may think of, so you could be asked to give examples of devices that actualize the TEM mode. So you can have a coaxial cable, which is still 2 conductors. You can have parallel plates. You can have a strip line. You can have a microstrip or a slot line. Okay. Because these are now 2 conductors which are not hollow in structure. You are not confining the wave to move in the Z only. So it means the wave is actually conducting based on the 2 conductors. So you can have an example where you have, you want to see what, in your notes, you can make a diagram or a drawing of how a microstrip look like and a strip line, the difference between a microstrip and a strip line. There should be a comma here for the parallel plate. So I'm saying that you make notes to differentiate between a microstrip and a strip line. Do you think air is a waveguide? ask a question. Do you think air is a waveguide?
I'd say it's not a waveguide.
Okay, why?
Because the waveguides have, let's say, the boundaries. If it's, for example, let's say a circular waveguide or a rectangular waveguide is like the boundary that define its dimension. But for air, it's just free space.
Okay, you can argue like that, but do you think in air there are different? Do you think there's a variation in the permittivity in air?
I'd say, yeah, I'd say, yeah, it changes.
It changes.
Yes.
So in that sense, you would agree it's a waveguide, isn't it? Remember, how do we make the waveguide? We make sure that the inner surface is higher permittivity than the outer one, isn't it?
Yes.
So that it reflects back into within the waveguide. So even in air, if you have different permittivities, the wave is going to be reflected depending on the permittivity in that region. So you can argue always, either way, you can argue either way. It looks like an open waveguide. You can determine the structure, but it's a very irregular structure for the waveguide. What about optical fiber?
It is.
Optical fiber is a waveguide. Okay. So for the transmission lines, whenever we talk about transmission lines, it's not just the thinking about the huge, in terms of dimensions. You also think about the small ones. So for transmission lines, you can think about coaxial cable, microstrip, and strip line. We also said initially that waveguide could be anything that's where the wave propagates, but you may also just want to confine it to some structure. You can say there's a rectangular waveguide, circular, or a ridge, or a flexible waveguide. It depends whether you want to bend the magnetic field or twist it, or the electric field. So there are many things that can be done to the waveguide. For us, it's just the design component that we need to learn. Again, it is conventional that we have, when we're designing waveguides, you always assume that the longest side of the waveguide is in the x-axis, so that A is always more than B. So we said last time that polarization, I don't know, I'm sorry, maybe it's not this class, I don't know. You may want to transmit your waves in a horizontally polarized manner or vertically. And in this way, you are able to transmit, just using one hardware antenna with two polarizations, you are able to transmit at the same time through what we call transmit polarization diversity. And sometimes if you want to transmit the wave secular, through circular polarization, you may need an antenna which is helical to do that. So the same way, circular waveguides are particularly designed for circularly polarized waves, or just to connect circular components like isolators and attenuators to rectangular waveguides. So when you do the analysis, here we have done the analysis through a rectangular coordinate system. We can do the analysis through circular system, and you will realize that, yeah, if you want to analyze waves that are circularly polarized, then you need that. We will be talking about the RI directions. When you talk about a ridge in a waveguide, you're just confining fields with a ridge inside the waveguide. Again, you can do the mathematics of that. So you can have either a ridge which is this is triangular, or it can be another rectangular ridge inside there. What do you think this would help us do when you have a ridge within the waveguide? look at, you can look at this dimension here. What do you think you'll be doing to the cutoff frequency if you place a ridge within the waveguide?
Because when we put the reads, we'll be maybe changing the dimensions A and B. So in some way we can change the dominant mode or the cutoff frequency.
Yeah, that's correct. So you can actually use a ridge. No, these are now manipulations that you can have. The equations become complex, but depending on what application you want to think about. So looking at just that cutoff frequency equation alone, you're able to do a lot of things and the propagation. So these two are the key that we are picking from here today to be able to use, as you will see in the examples in the tutorial. The other thing we said, we need to define a few concepts like a critical. By the way, the cutoff frequency can be called critical frequency. So I want us to define those two. Let somebody give us a definition for critical frequency or cutoff frequency. How would you define cutoff frequency in terms of attenuation? Cutoff frequency or critical frequency, what is the definition?
Okay, while defining the cutoff frequency, I'd say something like the cutoff frequency is the minimum frequency at which a particular mode of a wave can propagate
Yeah.
to a waveguide, and below which waves are attenuated.
Yeah, very good. Very good. Yeah, that's correct. I don't even know how to put it again. That is how it is. So below that cutoff frequency, if you try to propagate, there will be attenuation. Okay, somebody else, critical wavelength. In terms of attenuation, what is the critical wavelength? Similar to cutoff frequency, but can somebody explain critical wavelength? How would you define it? And I think I test this every year. Sometimes people miss a little bit. What is critical wavelength?
The maximum wavelength at which waves propagate in a waveguide and above which all waves will be attenuated.
Correct. Good. All right. What about group velocity? So we have the critical frequency, you have that, or cutoff frequency, critical wavelength or cutoff wavelength, you're able to define. So group velocity actually is the signal propagation velocity. So you assume that a signal is composed of narrow band frequencies, which is centered around some f. So if you average all those frequencies, okay, then you get f, which is the center frequency. So you can actually determine the group velocity, which is the velocity at which the signal propagates, or the speed of energy flow in the waveguide. So when we say that this wave is moving at this speed, actually it's the group velocity. But the phase velocity, you choose a constant phase of a point in a particular mode. Now, this is I will give an example. So if so the phase velocity is the speed of a constant phase point of a particular mode. Now, I want to ask a question. Do you think the phase velocity could be higher than the group velocity? There's a point there, the speed at which that phase is changing, and then the velocity of the wave. Do you think the speed at which the phase is changing could be more than the group velocity, the speed at which the signal propagates.
Yes, the phase velocity can be greater than the group velocity.
Okay, and I think this you would be asking physics. Do you think if you are in a bus, you can move at a higher speed than the bus?
Depending on the reference, someone who is outside my reference, of course, will see me moving faster than the bus. But while inside the bus, maybe the bus is stationary, so technically I can move. For example, if I run in the bus, I'm technically moving. Okay, it's a confusing topic.
Anyone else? So do you think you when when you are moving, when you are walking in the direction of rotation of the earth, do you think you're faster than the earth?
No.
Huh? Why not? So again, it depends on the reference. I think the guy who said it first said it very well. It depends on the reference. So you are watching this face moving on this wave, which is also propagating. So that rate of change of that point gives us the phase velocity, the rate at which the phase is changing. It is possible that it can be more. And we will have equations that actually relate the phase and group velocity. What about evanescent mode? What do you think? Because we have talked about a mode being at a cutoff and at a higher cutoff frequency. What about evanescent? What does it mean?
Okay, I think that a mode actually becomes evanescent when it actually propagates below the cutoff frequency, so that it becomes non-propagating.
Okay. So it's evanescent when it propagates below the cutoff frequency, and now the mode becomes non-propagating. I want you to repeat that again. It is propagating below the cutoff, then you're saying it becomes non-propagating. Do you want to add more meat there so to differentiate the two propagating that you have used, the words propagating? Because you have talked about propagation twice. So does it propagate and becomes non-propagating? Or what did you want to add to it?
I'd say maybe they are diminishing modes.
They are diminishing modes. Remember, this is energy. So when it diminishes, what happens? The energy must be transformed, isn't it? So if it was diminishing, that would be a different thing. We are just saying that you are injecting the wave at a lower frequency, which is below cutoff. You look at this one. What happens to beta when you have a negative value here? It becomes imaginary, isn't it? So what you're just trying to say in real sense, physically, what is happening? When F here is below cutoff.
The wave vanishes.
So when it vanishes, where does the energy go? Because remember, you're exciting this wave at a certain power. So there's energy. It's just like asking you. I was actually recently doing something on what they in power system they call power factor. You can have some angle here where you have real power and apparent power. Apparent power and the reactive power. When we say reactive power, what is really happening to the reactive power? What is this reactive power? What happens when you have a reactive power to the energy flow? Remember, reactive power is just like having a capacitor or an inductor. Someone wants to try?
It absorbs power from the circuitry, does not send power to the load.
It does not send power to the load. So it absorbs power, and then in the next phase, what does it do? Because remember, AC power will change the phase, isn't it? From positive to negative. So what happens? If you have a conductor or no, a capacitor or an inductor which has absorbed the power, in the next phase, it changes the polarity. The next phase, like that. So what does it do to that power? When it absorbs it, it energizes, or the capacitor is charged fully, or it energizes the inductor. But when you change the polarity, it sends it back into the source, isn't it? The generator. So you have generator. Say you have your resistor there. So the resistor will have its P, no problem. Active power will be dissipated. But here, in one cycle, you are retaining power there. It's energizing it. But because you are going to change the phase, the dissipated one remains the same, but this one will now go back. So you're actually sending this power back to the generator. It's like a reflection in the transmission line. So you can store it and then send it back. Store, send back. So it means you're actually going to retain some reactive power at the load. So if you retain some reactive power at the load, it means even at the source, to balance that reactive power, you will be actually having some reactive power also at the source to balance that one at the load. So what is actually happening before, we don't have to go into this. I was trying to convert this active power P, because P will remain to be here. Then you have another R. But this reactive power now is in terms of watts. You can see still P plus this new R here will still give you S. But that's not for this discussion. So what happens is that when you have that cutoff frequency being, the frequency being below cutoff, the propagation will still be there. But as you inject, the propagation will be happening backwards towards the source. All right, so that's why you have, if you have a negative here, you have a J. So beta is J something. So it's a backward, it's a reflection towards the source. So you inject and then it comes back, inject and come back. So there's a backward propagation. So there's propagation. As much as we are saying there's no propagation, what we mean here is there's no forward propagation. All right, is it clear? This, yeah. So evanescent mode, no wave propagation at all. You will see that in the text many of the time, that it is totally attenuated, but in real sense, it's actually just propagated backwards towards the source. So next time we will, you see, so the energy of an effervescent mode is not lost, the energy is transferred back to the excitation source. Okay? So there's a constant exchange of energy with the excitation source. So you excite and then come back, excite and come back. So it's just fully reactive power. So next time we look at excitation of waveguides, how do you excite the waveguides to ensure that you achieve those modes? And that next time should be tomorrow. I hope we'll have the class online. So I will go through excitation and it's just 1 hour. Excitation is not so difficult, just a simple example. Then we look a bit on power flow within the waveguide. Okay, excitation and power flow tomorrow. Remember, the waveguide could also have some impurities on the conductance, on the conductivity. So if it is not highly conductive, we will see if there are some impurities. How do you compute the amount of power that propagates within that waveguide? So we'll see where we reach tomorrow. After that, we go to the resonant cavities, and then we let you continue with your group work. So the class rep, you are talking about the groups and the topics. Can you agree among yourselves? I suggested how many groups?
I had suggested 6 groups.
6 groups. Eh?
Yes.
I want to leave that because here is basically you guys being the tutors. I want you guys to do all that work.
Okay.
Gain some insight. So you're called Sefin.
Yes.
Yeah. So we have 6 groups, and then of probably about 7 members, and then they try to divide those topics among yourselves, and then let me know.
Okay.
Yeah.
Yes.
Okay. Fine. I don't know whether there's a link for tomorrow's. I think I should have created for tomorrow's class. Yeah. Okay. All right. So we try to join tomorrow again. I don't know. We are on strike, but I think because of we are starting the semester late, so we'll just have our class going. So let's have the attendance if there are no further questions for now.
Yeah, I had maybe a question or
Yeah.
yeah, if you could talk about the surface impedance, wave impedance, degenerate modes.
Yeah. Now we will don't worry about those ones. We will get it when we are doing degenerate modes and the impedance when we are doing the power. Okay. For the definition of the concept, that's what you meant, isn't it?
Yes.
Yeah, we'll handle them. We'll just be taking notes on them.